Sure, whatever. No, wait, I take that back. I forgot. Okay, quickly, guys. Let's just recap. The Michelson-Morley experiment, two things really occurred, Zach. Shush. The first thing was that it was a null experiment. It showed no interference patterns. That the light was not traveling slower when it was trying to travel upstream, and it wasn't traveling faster when it's traveling downstream. In fact, it traveled the same speed in both paths. Okay? So, Andrew, could you shut the door but not lock it, please? Andrew, shut the door. Alex, sorry. Alex, calling it. Wrong Zhang. Thank you. So that's kind of like the travelator question. You would say definitely the bloke that walks wins, but then it turns out they both arrived at the same time. So the crossing the stream kind of question absolutely didn't work. So this is the famous second postulate. The speed of light, this is what Einstein said in his second postulate of special relativity. The speed of light will be the same for all observers, no matter what frame of reference that they are in. So that is the weird one. We spoke very briefly at the end of the lesson that if you threw a ball on a skateboard, you combine the velocities together, you add them. But with light, you don't. So if you're traveling at relativistic speeds and you shine a laser pointer, it does not appear at an increased speed or a decreased speed. It will always be observed at the speed of light, c. This gives us a few weird phenomena that we don't often detect because we don't get to fast speeds macroscopically, but little particles do. We can get little charged particles up to very, very fast speeds, and so we can confirm via experiment Einstein's postulates and the consequences of. Now, there was talk, I see, yeah, you put your hand up before and then you put it back down.
Do we assume that in a vacuum on a skateboard is the question of the state?
It's an imaginary skateboard that can get up to that speed. Yes, in a vacuum. Because if it got up to that speed in air, it would burst into flames and vaporize every particle. Yeah. So you wouldn't see a baseball, you just see a big bright flash of death, plasma. Okay. There's a very good XKCD website on what could happen if you threw a baseball at that speed, but let's not talk about that. Let's talk about inertial frames of reference. So, oh great, I didn't even work it out last year, so here we go. Simultaneity occurs when you are in the same reference frame. You would agree that two events occur at the same time. They would said to have occurred simultaneously. So, ignore this bloke. I don't know why I put him out there. Let's say, in this first example, we're in the same frame of reference. So both of these people are at rest relative to each other. And two lightning bolts just happen to flash and strike the ends of each carriage. Okay? Now, obviously, the path lengths L and L are the same for both of them. All right, so that's, this guy here would travel L on 2 to get to the middle, L on 2, and then the guy outside the carriage, well, a little bit of trigonometry, you could see the path lengths are the same. So really, we could say T1 equals T2. What's our equation? T equals S on V. So we could say L1 on 2 on C would equal L2 on 2 on C. Or just L, I guess. L on 2. Path, yep, L on 2. And this guy down the side, yep, they would both agree that they saw the lightning strike at exactly the same time, simultaneously. Okay? But because light does not travel at an infinite speed, basically the invariance means finite, okay, and constant in both frames of reference. Let's look at this consequence down here. Suppose now, you got to be lucky for this to occur, so that's why it's just a thought experiment. Imagine two blokes that they line up, and just at the time that they line up, flash, we get two lightning strikes. Sometimes they talk about camera flashes or laser beams. Two lightning strikes, both ends of the carriage. Now for this guy, obviously again, path length, don't draw that because I'm deciding to change my mind. The path length to this guy is going to be the same. So again, he would go, it happened at the same time. He would agree from his observation, if he's at rest with the lightning flash, then he would see them happen at the same time. But in that time, this train has advanced forwards by a certain distance. I'm guessing that it's probably V times T, so that's C times L2 on C. Well, hang on, that doesn't work. Distance, velocity times time. That should be it, shouldn't it? Oh, velocity, try that again, sorry, times time, all right? It's gone forward, which means he's actually approaching. This guy is now a little bit closer to this lightning strike. He would see that flash first. And he's a little bit further from the back lightning strike. So here, again, this is the idea of Galilean relativity said that they're both making observations from their own frames of reference, and they're both correct. One says that the events occurred simultaneously. This guy here said same. And this guy here is saying different. Okay? So if you take your measurement inside the train, you are correct. They happened at different times. If you take your measurement outside the train, you are correct. They happened at the same time. Strange, huh?
Why does the person in the train see them as happening?
Because these lightning strikes are basically at rest, so that they're in the same reference frame as the lightning bolt. Okay, so he's in the same reference frame. They just happen to strike the outside of the carriage. And then as the light's travelling towards the bloke in the train, he's moving towards one of the light sources.
But wouldn't that still mean that if the speed of light's approaching him, wouldn't that... I thought that the laws would still mean he sees the light at the same time.
Nope. They would reach him at the speed of light.
Yeah.
But the time taken for that light to travel to him, he's moved by this amount. So one light gets to him faster than the other because the forward lightning flash has to travel a shorter distance. Okay? Yes, Georgie?
Can you have a sort of reverse Doppler effect where the observer is moving and not the source?
Yes. So let's... We could flip this reference frame. Let's have the bloke outside moving past and the guy inside the carriage is stationary. Then their observations would change.
Since the person inside the carriage is moving towards the right lightning bolt, would there be like any blue shift? Like obviously not.
Yeah. So the Doppler effect does occur with light, and it is used to measure advancing and recessional speeds. And we might look at that when we look at, in our last week of the term, we look at cosmology. Okay. Now it's way at the end of the term, but basically our test is in week 8. Because we're not allowed to test you in week 9 because, too much. So we test you in week 8. And the only common assessment period on that day is Monday and Tuesday. So we test you on Tuesday. So we've got a week and a half where we just sit here twiddling our fingers. No, we're going to teach you cosmology in those week and a half. And since we haven't tested it in the Unit 4 test, you can expect that it might appear in the end of year exam. Okay, but anyway, let's get over to some fun stuff. Einstein and his Gedankens. Get over to this page, please. Now, Gedanken basically means thought. So he did lots of thought experiments, and Einstein was incredibly good at making up thought experiments and then figuring out the mathematical consequences. Okay, so we are going to the Lorentz factor. We're going to derive the Lorentz factor, but you don't need to, it's not expected, but it's in the data sheet. But I'm going to show you, this is the simplest way of showing you the Lorentz factor, okay? So, we have our imaginary train in our Gedanken experiment, and it's traveling forward with a velocity, okay? Now, the train has a height of length L, and inside is a bloke measuring a flash of light that travels up to the ceiling. Okay? Now, he is going to measure T naught. Okay, that's his thought bubble there. Let's put T naught to a definition. T naught is called the proper time. That's the time measured, or stationary time. Time measured in same reference frame.
Is it technically, it's just when two events occur in exactly the same position?
I don't know. Let's just call it stationary time. Proper time is when we measure it where the event is occurring. Okay? So again, Galileo said, let's just imagine that we do this experiment right now. There's a laser beam on the floor and it shines up to the ceiling, and we measure the time for that light to strike the ceiling. And our knowledge, velocity over distance over velocity, length over c, you'll get the time. It'll be very, very short, but we can measure it with laser beams and photo gates and things like that. Okay? Now, we're going to have a look at another bloke outside the train, and he's going to observe this event through a very, very accurate and fast-moving telescope. And with his stopwatch, he's going to measure another time in a different frame of reference. Okay? Now, just like Galileo, you're dropping the ball on the ship, and somebody on the shore would see it travel in a parabolic arc. What this guy sees is the beam of light travels the hypotenuse. And in fact, it's travelled v in a time t sideways. So the train moves sideways in a certain time period that he measured. That was the time from the light to leave the laser and strike the top. He goes, dink, that's the time. And I know the speed of the train, so it's advanced forward by vt. Okay? Now, the laser beam travelled at the speed of light, ct. Also, it travelled at the speed of light for the bloke inside, ct naught. Okay? So, here's where Einstein's first postulate comes in. Both of these are observing the speed of light travelling at the same rate, c. Okay? So they both see the laser beam travelling at 3 by 10 to the 8, but this guy outside saw the laser beam travel a longer distance. So they're going to get different times. They're going to get different measurements because they are in different frames. Okay? And the next thing is, Einstein said, well, this is okay because the first postulate says that no frame is better than another. Both are correct from their own frames of reference. I should have said the second postulate is that the speed of light is a constant measurement of c no matter what frame that they are in. Yes, Mr. Rahal.
Is there a reason why we use uppercase T for time, or is that just in this?
No, makes me feel good. You could use lowercase, doesn't matter, the T for time period, okay? So, let's just redraw this triangle again. We don't do that. Let's draw this triangle again. We're going to have CT naught, and then we're going to have CT, and then we're going to have VT. And that should also be red. Yeah, let's make that red. Okay? Now, we bring in some Pythagoras. L squared plus x squared equals a hypotenuse squared. I just made up another x term. That's x. Yeah. And L is the height. Doesn't matter. We're not going to use that for long. Let's throw in our terms. So L is going to be CT naught all squared plus VT all squared equals CT all squared. Then we're going to do some mathematics. We're going to divide through by c squared. So we'll get c squared, wait a second. Yeah, I'm just expanding, calm down. T naught squared plus v squared t squared equals c squared t squared. Then we can divide by c squared, okay? And we get a cancely, but not a cancely there. And we get a cancely there. We've got the whole page, so let's just tidy things up. t naught squared plus v squared on c squared t squared equals t squared. Let's throw the t squared terms on one side. T naught squared equals t squared outside of 1 minus v squared on c squared. So I took the v squared on c squared t squared term over, it becomes negative. Then I factorise out a common factor of t squared. Yes, Tobal?
So the t's for c and v are the same. Stuff all
The t's for v and, well, one of them is.
is the same.
Can I get to the end? We're nearly there. I'm going to put t squared on its own, and that's going to be t naught squared over 1 minus v squared on c squared. And then lastly, I'm going to take the square root. So t equals t naught over square root 1 minus v squared on c squared. Now, this is the equation that compares both times due to the motion of one relative to the other. As I should hopefully have shown you in that diagram, they're both taking different measurements of time. From their frame of reference, they're different. They're not the same. Okay, I'll get to that in just a moment. Just look at this. If v equals 0, that's the train has stopped, and then dink, the right-angled triangle becomes just a straight line. He sees a straight line, he sees a straight line. Their time is the same. They equal each other. But as one starts to move fast, then the bloke that's the bloke that's moving relative to the action sees the hypotenuse. Okay? What we will find is, have a look at this. As v gets bigger, this term becomes smaller, and the square root of a small number is still a small number, and so he will observe the time to be greater than the proper time. I'll attempt to explain it a little bit better. Now, by the way, we can tidy this up. We can say that t has been changed by some constant, gamma, where gamma is known as the Lorentz factor. And so that's just 1 over square root 1 minus v squared on c squared. That's called the Lorentz factor. Okay? So throw that down in a lovely highlighted. Now this is really, really cool because it sets the speed limit. Before I go back to the diagram, let's look at this Lorentz factor. It basically prevents you from breaking the rules of traveling faster than the speed of light. Have a look. As your velocity approaches c, the limit as v tends to c, that's going to approach 1, and then you get 1 minus 1, which is 0, and then you get the inverse of 0. This Lorentz factor becomes incredibly large, okay? And we'll look at the consequences of that. Time stretches out to infinity, length is compressed down to 0, momentum approaches infinity also. So you cannot ever get faster than this, and no experiment, no phenomena or observation has ever seen any particle travelling at the speed of light except for a photon that has no mass. So basically, this is the speed limit for anything with mass. We can't even get to c. We can get to 99.999999999%, but then this Lorentz factor gets really, really big and it becomes tricky experimentally. So let's just go back and I'll try my best to explain why they're measuring different things. You have to imagine that the photon of light has its stopwatch, and the stopwatch is moving. And so you go, the bloke on the train says it took, let's just say 1 nanosecond. He goes, all right, I measured the time for the speed of light to travel 1 nanosecond. The little photon that's traveling from floor to ceiling has its watch and it's moving up and it's going 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. When it gets up to 1.0, spank, it hits the ceiling, okay? Now, this guy observing the photon, after 1 nanosecond, the photon's not at the ceiling. The photon, I just shifted that. The photon is kind of like there. if we just sort of slide the adjacent across to the hypotenuse. And so you go, well, if the photon was there at 1 second, it's going to have to take a little bit longer. And the hypotenuse is extended by the Lorentz factor. It might take, let's just make up a value, 1.5 nanoseconds. So here's the crazy thing. Both observers are correct. The bloke outside measured the light to take 1.5 nanoseconds, and he is correct. And the guy in the train at rest with the action measured t proper to be 1 nanosecond, and he is also correct. They are both correct. Isn't that strange? Over the page, I would like for you to go over another page. The simplest way to remember this fact is that moving clocks tick slower this is a bit weird now. The stationary observer in the diagram was the bloke in red, and he was watching the moving clock, okay? So if a moving clock whizzed past at a certain speed, you would look at your watch and go 1 second, and you would look and it would only have read 0.8. You go, well, that clock's ticking slower. Okay. Let's just throw in the equation that's in your data sheet. Hasn't changed since the 2017 data sheet. Let's just write down what you have, because there are different variants of it. Oh, there it is. You're not given the Lorentz factor. All you are given is t equals t naught over. Okay? So you're not given the Lorentz factor. But you should be able to take T naught outside, throw him down here, and then you're left with a 1 over. All right, and that's the 1 over, the blah, blah, blah. That's the Lorentz factor. That is all you've been given. But there's a bit more room in the box. So let's just say T proper equals the T naught, proper time.
Questions when we're writing out the forms, like initially, do we have to give them exactly on the data sheet? Or we just go T equals gamma T?
If you did that, I would say where gamma equals 1 over square root. And I use what? Hey, thank you. Hey, ooh, that would break all of Einstein's rules. Now, no, Mr. Rahala, you're on a question ban for a few moments. Let's look at this page, please. This is a nice, interesting table and graph of the Lorentz factor. Now, by the way, sometimes you will see in some books, they would say beta equals V on C. And so sometimes you see Lorentz factor is 1 over square root of 1 minus beta squared. Now, I'm going to show you the easiest way to use this equation is not to express V as meters per second and C in meters per second, because then you have to go 2.7 times 10 to the 8 bracket squared divided by 3.00 times 10 to the 8 bracket squared. No, if you're at 2.7, that's 90% the speed of light. Your beta term is 0.9, and so beta squared is 0.81, and so I know now it's the square root of 1 minus 0.81. Right? The math is a lot easier if you leave V as a ratio of C. Now, this is a nice little graph that shows the Lorentz factor. Basically, the beta, or the V on C, really starts to become big after about 60% the speed of light. But for us, remember I said it becomes significant to the third sig fig at around about 10%. Where's 10%? There's 10%. That number there. Oh, look, the gamma factor is 1.005. So if you're timesing a number by 1.005, chances are it's going to, that's not the right one, chances are it's going to affect that third sig fig. Okay? So, let's do an example. Let's go back to this page and hope that you have some room somewhere. Let's throw in a value. Okay? So let's say that the train is traveling at relativistic speeds. Let's go 0.85 c. All right? Now, you'll need your calculators out. I've got one here. I'm running off script a little bit because last time I didn't do it as fast as that. Let's say that the bloke inside the train measures it to be a nanosecond. All right, so let's go T0 equals 1 nanosecond. 1 times 10 to the negative 9. That's pretty good. That's a short roof, isn't it? 1 meter would take 1 over 10 to the 8. Anyway, so let's work out. We know that this bloke is observing a moving clock. He's going to see it take a longer time than 1 nanosecond. Let's calculate it. T equals T0 over. So here I would say, well, since we've got V equals 0.85 C, V on C is 0.85. Therefore, V squared on C squared is 0.85 squared. I wouldn't go 0.85 times 3 equals 2.65 times 10 to the 8 because then your calculator, your fractions are going to get huge. You're okay to do 1 nanosecond over square root 1 minus 0.85 squared. Don't be daunted by this nasty looking equation. It becomes very simple. I'm just going to leave the nanosecond out. 1 over the square root of 1 minus 0.85 squared gives 1.898. 1.90 nanoseconds. My Lorentz factor was 1.9. You could check that. Lorentz factor equals 1.90. Okay? So if you are travelling at 85% the speed of light, the time would appear to slow down by that rate. So the bloke outside the train would go, right, I'm at 1 nanosecond. Let's look at the photon's stopwatch. Oh, hang on, it's at 1 divided by 1.8. It's only at 0.4. And then he keeps watching it. 0.4, 0.5, 0.6, and then eventually it seems to strike the ceiling at 1.9. Yes, Mr. Rahal.
In an exam, can you write V squared and C squared as beta squared and put that into the equation?
No, I'd prefer you didn't because this is in the data sheet over here, bottom right. So let's just stick with if you've got that there, that's fine, that's perfect. I wouldn't risk going straight to that. But just show the ratio of V on C, and then V squared on C squared equals that. You've done enough mathematics. Okay? So, here is, that's pretty much a good graph of the Lorentz factor as we get closer to the speed of light. Let's get over the page to... But when does it become... Here we go. Can we go to page 20? Now, we could have used... I'm going to use the time example here. Okay? When does it become significant? So, let's go that... Let's say t proper equals 1.00 seconds, a nice round number. That means our observed time would need to be greater than 1.005 seconds. Because if we increase that 5 by the slightest amount, then we would have to round the third sig fig up to 1. Does that make sense? Yes, it does. If it's greater than that, then 0 rounds up. Okay? So, at what speed do we need to consider Einstein's theory of special relativity, because it's now changing our third sig fig. Now, oh, by the way, I'm going to throw the equation down again. Don't be scared by this equation. Don't worry, I'm using capitals I probably should have used. Now, the easiest thing is if you are given V and one of the T's, it's very simple. You can just rearrange for T and we're good. But if we have to rearrange for V, it's just a whole lot of arithmetic. We've got to pick it apart and do all of the reverse BIMDAS to get V on its own. That could be done in a test or an exam. It could be a 3-mark question. Here's V and here's one of the times. Give me the other. 3 marks. Equation, substitute, solve. If you were given a proper time is this and an observed time was that, how fast must it be travelling such that these two times were observed differently? That's going to be adding a few extra marks of rearranging. Okay, that could be a 5 or a 6 mark question. So let's get about doing it. We want t on t naught equals 1 on square root 1 minus v squared on c squared. Let's flipperoo. T naught on t equals root 1 minus v squared on c squared. Let's square both sides. And we get t naught on t all squared equals 1 minus v squared on c squared. Look, we're nearly there. Then what? V squared on c squared equals 1 minus t naught squared on, I forgot to put the square outside, don't matter. And then v on c equals that. And we could probably just throw all the values in there. And I realized I had a quality there, and I started with equal signs, but doesn't matter. Well, let's just find the speed at which it equals. Let's go square root 1 minus 1 on 1.005 all squared, and we get 0.996. V on C equals 0.996. V equals 0. Oh, I forgot a 0. Damn it. 0.996, which is roughly 10% the speed of light. So that's the number that I might have shouted out to you earlier this term. Providing our velocities are below that, you don't have to worry about any Lorentz factor or relativistic effects. You can just go t equals t, e equals a half mv squared, it'll be travelling that fast. Done. Once you get above that, then you've got to start using the Lorentz factor and things get trickier. Okay? Are we happy with that so far? Let's look at some examples. Actually, let's get to length contraction. No, actually, let's get to muons. No, let's look at this example. Okay, again, these are all Gendankens. You will not have a pendulum of a grandfather clock with a period of 3 seconds travelling past you at 95% the speed of light. Because you're not going to be able to observe it for that long. But again, it's a thought exercise. It works on particle scales with nano and microseconds. It also works for grandfather clocks. So, this is really easy. I stole this from my modern physics textbook. They've gone gamma t prime, t proper. You can see there's your gamma. They've just put t proper out the back. You could throw the t proper on top and it'd just be 3 seconds divided by. But the reason they've done this is because at 95% the speed of light, it tells us that the Lorentz factor is 3.2. That is the factor by which time is dilated. So the moving clock appears to be ticking 3.2 times slower, and so it would take 9.6 seconds for a full period of pendulum to occur. Okay? Now, most textbooks will give you the muon as their example. I think the Pearson Science textbook does it. The Modern Physics textbook does it. Muons basically support, not prove, but they support Einstein's theory of special relativity. And here is why. Muons are very, very heavy electrons. They're in the same family of particles as the electrons. They have the symbol mu. Hang on, make sure I get this right. It is muon. Mu negative. So that's a mu. Try that again. There it goes. That'll do. And they're very, very heavy and they're very unstable. And they decay after a time of about 2.2 microseconds. But what's happening is that they are formed up in the atmosphere when atoms are struck by high energy cosmic rays that are flying around in space. Some of them come down and hit the atmosphere and dink, you make this high energy muon. And he loves travelling at a speed speeds of around about 0.996 or 0.99 c, around 99% the speed of light. Okay? Now, they are made really, really high up. We're talking, on the order of 10,000 meters up in the atmosphere. Our atmosphere extends up to about 40,000 meters. But let's just go, okay, how long would this bloke live? Well, V times T, so how far would this bloke travel if he only lived for 2 microseconds? So we'll go our 0.99 times the speed of light multiplied by 2.2 microseconds. It turns out, I'm going to go approximately because I'm going to use the same value that's in the diagram. Okay, you do it in your calculator, you'll get around about the same answer. Okay, 2.2, a little bit more, a little bit less, I don't know. Now, if that was it, if we left it at that, the muons would never get to the surface of the Earth because they are made 10,000 meters up, they would die 9,500 meters up, and we would never detect them down on Earth. But we do, because they are moving relative to us down on Earth. So if we stand here with our telescope and we measure the time of the muon's clock, we're going to see that the muon's time is dilated. And it's dilated enough that the muon reaches us. So let's go 1 minus v squared on c squared, 2.2 microseconds over 1 minus 0.99 squared. Wouldn't you know it, we observe the muon. Ironically, its symbol is mu, and it lives for a time whose metric prefix is also mu. That is purely a coincidence. We see that muon travelling to us at 99% the speed of light and living for 15.6 microseconds. So if you ask the muon, just as it's dying, you'd say, quick, look at your clock, and it's like, 2.2, poof, and then it disappears. But we watch this muon travelling through, and it gets to 15.6. You go, well, how far would it get? S equals V times T, 0.99. Basically, you multiply that length by the Lorentz factor, which is approximately, 8. Anyway, let's just do it. We already did it. 3 by 10 to the 8 times 15.6 microseconds, and it gets to approximately 4,700 meters. Now, I kind of lied a bit. That time is its half-life. All right, so half of the muons would have died. The next half will die in the next 15.6 microseconds, and then the next half of the half will then die. And then I think here's your graph. There's your muon at rest, dead. None get to Earth. Here's your muon traveling at that speed. These guys down here are detected. Okay, so classical mechanics says that no muons should be detected down at Earth. And yet you point your muon detector up and we get these streams of muons striking the surface of the Earth. Okay? Isn't that fun? So there is our example. And I'm going to use this example to explain the next phenomena. So T proper, gamma. You can use that equation, and I've got a whole stack of questions in this booklet that you can look at, calculating the time for each reference frame. But do you notice something strange? Basically, the postulate number 1 says that both the muon's frame of reference is correct for the muon. He lived for 2.2 microseconds in his frame, and us down on Earth, we are correct that it lived for 15.6 because no frame of reference is considered better than another. Okay? But look here. If we said, if the muon lived for only 2.2 microseconds, in order for him to travel that 4,700 meters, we have to make it so that he can get... So we've got to squish the length that he's traveled. We need to contract that length for the muon. From the muon's frame of reference, he does not travel 4,700 meters. His length is going to be contracted by the same factor that time was dilated. Okay? So the Lorentz factor comes into play here. Now, let's do some maths down here. We're doing a lot of relativity in one lesson. Okay, so now I did the derivation the other day and I've forgotten how to do it. Okay, anyway, let's just say that we know L proper is the height of the mountain. When we measure a mountain, we're normally stationary. We're not racing past it or towards it or away from it at 99% the speed of light. So that's your proper length. Okay? Now, your observed length, so how can we figure out S equals V times T? So maybe L would equal V times T, and L proper would equal V times T proper, I think. And I'm going to stuff this up. I was going so well. Basically, what are we going to do from here? L equals L naught common V equals L on T, V equals L naught on T naught, cancely, L on L naught equals T on T naught. No. L equals L naught T on T naught. Okay, hang on, we're nearly here. And T on T naught. Hang on. T on T naught is the inverse of gamma. I've got it. We're back on track. T on T naught is the inverse of gamma. So the inverse of the inverse is this bad boy. Right? So we do an inverse of an inverse and we end up getting just him. And so L equals L naught times 1. I've got it. I mean, it's done. We're done. QED.
T on T naught is gamma, and the reason it doesn't work is because your proper time is not in the same reference frame as your proper length. So I think they should be swapped.
Okay. So L equals T proper.
So
that way. Damn it! I almost got there.
Proper time is when it happens in the same place in the reference frame.
Yeah,
so
no.
If you're following it with the muon,
All right.
your proper time would be in the reference frame with the muon moving.
Put that in a box. There's your equation for length. There's your equation for length contraction. Okay? So instead of your length increasing by the Lorentz factor, it's decreased by the Lorentz factor. Okay? So up top there we said that the time of the muon dilated by a factor of about 8-ish, or 1, or whatever it was. Then according to the muon, that 4,700 meter mountain is going to be contracted by the factor of 8-ish. And so he sees it as 650. Okay? So this is the crazy thing. From each frame of reference, they're both correct. The moving particle sees the length contract, whereas the stationary observer sees time dilated. The stationary observer is not going to look at that mountain and go, oh, look, the mountain looks really, really short. It sees the effect of time being dilated. Meanwhile, the muon goes, no, time's not dilated, but the length that I travelled was contracted. Yes, Max?
So, I mean, if we were asked in the exam to calculate what the length would appear to be, could you just use the classical mechanics method instead of going through that?
Yes, and you've got to be careful. Sometimes they'll try and trick you. They'll say, calculate the length of the mountain as observed by the person on the ground. Well, it's that number there. Right? There is no calculation. It's that. Right? So just sometimes they'll try and trick you by asking for the time that's already given, or the length that's already given. Let's just confirm, just check that our equation comes out. Let's just go proper length times or divided by the Lorentz factor. And I'll erase you 4700 square root 1 minus 0.99. Okay, close enough. So roughly 650 meters. So we did round those values slightly. Okay. By the way,
with those questions where they try and trick you, would that be worth 1 mark?
probably, yeah. So you can almost see, it won't even say calculate, it might just say state. Yeah, it's hard to trick when it's a 1 mark question and it says state and not calculate. But
So it's like a table of values to fill out, like 6 values for the report.
all right, here, gamma, length contraction. Please just highlight. Whoop, don't do that. Please highlight. It only contracts in the direction of the motion. Okay? So there's an example of if you had like a spaceship that looked like a triangle traveling Vx with dimensions x and dimensions y, it is only Lx. Okay? So the contraction will only occur all right, in the direction of travel. So if you see something whizzing past you traveling left, then it's the left dimension that appears to be contracted. Okay? And in this box, we'll write the equation as it appears in your data sheet, but we've run out of time. Yes, Tobar, how may I help you?
When the mirror is going down,
Yes.
does the ground appear closer to it?
Yeah. So imagine running towards the back of the room, and the faster you go, the room suddenly squishes. Somebody made a really cool indie game where you can run at relativistic speeds, and if you run towards things, are blue shifted, and as you travel back, they're red shifted, and the dimensions contract and stretch out as you move around. It's an interesting game. I think I found it, and I'll put the link up. But we've run out of time. I'll kick